That's right.
Ladies and gentlemen, if you will take your seats, we will resume our program in just a moment. Please take your seats. Thank you. When my love tell you a tale, boy and girl, and their love story, and how he loved her oh so much, all the charms she did possess. This did happen once upon a time. Things were not two of them.
How do I pronounce this girl's first name? I think so. I've only chaired like twice. I'm fairly nerve-wracking. It'll be right behind you.
Look at the floor.
Guys, welcome back. We will continue with our final two talks for this session. Before we get going though, just a reminder that if you collected trading cards last night, take a photo and send them in. I've heard there's only 2 submissions, so if you want to be Duckmaster, the opportunity is still ripe and prime. So you just need to email that by 11 o'clock. Someone saying no, they've submitted, so you've got to give her a run for her money. So we've had a powerhouse session of women this morning, and we're going to move on to some of our gentlemen. Our next speaker is Derek Smith from the University of Cambridge, and he'll be presenting on patterns in and the predictability of the antigenic evolution of influenza and SARS-CoV-2 viruses.
Thank you so much. I'm going to be doing a sort of a comparative analysis today of the evolution in bird systems. This is an antigenic map of the SARS-2 viruses, including the Omicron and BA.4/5. These are data generated by Shauna Shen and David Montefiore at Duke University. Just a little quick orientation. The original wave 1 virus is here in dark blue, alpha here in this green, delta here in these brown viruses, the beta virus up here, the 526 before 4K here, The kappa here and the lambda, and then the BA1 here, the BA2s sort of around in this area, and then the BA5 up here. Let's put that in perspective with the influenza virus evolution. On the left here is the antigenic evolution of the H3 influenza viruses from 1968 through to 2002. And on the right is the influenza B antigenic map that Kuan-Fu showed yesterday with the early Victoria and Yamagata antigenic clusters. The grid in the background, I'm not sure if it comes up across on that projection, it comes out just fine here and on the screen here, is a twofold dilution in whatever assay is being used. In this case, it's the HI assay. If we put these on the same scale, this is what we see. And we see here something that we see pretty much in every system that we look at, is that the size of these antigenic clusters is around about the same. Sometimes it's a bit bigger and a bit smaller. Sometimes there's some sort of a couple of subclusters with a temporal separation that join up. But oftentimes there are these big antigenic changes between clusters, which are enough to warrant an update of the vaccine. And these changes, you can see, are about the same size for the B viruses as they are for the H3 viruses. There's variability from cluster transition to cluster transition. And this is pretty much the same whether or not Nicola Lewis looks in equine flu, whether or not people look in other systems, and through to the present day in the H1 viruses, etc. Let's put the SARS-2 on that same perspective. So on the right-hand side here of these three different SARS-2 maps that I'm showing is the map that we were just looking at, but just highlighting the wave 1 here, the alpha right next to it, the delta just below, the beta up here, and the Omicron BA1 to the right. The map in the middle is from Janine Innsbruck's laboratory with data generated by Annika Rosler in Innsbruck. And on the left is the data from Megul Suthar's laboratory with data from Megul and from Venkata there. And you can see there's a little bit of difference between these, but overall the relative distances are around about the same. And this is about the same sort of variation that is seen between one good flu lab and another good flu lab. One of the differences here between the Emory data and the Innsbruck data, and then the Duke data, is that the Emory and the Innsbruck are a live virus, and the Duke is pseudotype. And one of the things about the pseudotype for BA1, especially this pseudotype assay, which was done on cells that do not express TMPRSS2, is that they estimate the antigenic distance from the wave 1 viruses, and thus the vaccination immunity against wave 1 to BA1 to be a little bit less than for the two live virus assays on the left. I put these like this and on the same scale so that we can see about the magnitude of the differences, and we see that these changes, that maybe the beta change and these other variants here that oftentimes, well, they do all have substitutions of 484. That there may be, sort of just on the edge of being a cluster transition, or perhaps a mini cluster transition. If we look, for example, at this Victoria strain here, maybe they would be on the edge here. But if we look at the distance to Omicron, the red strain on the right, then we've got something that's about the size of a cluster transition that we see in flu. Of course, what we don't know here is just how much a twofold dilution in the assays that are used for SARS-2 correspond to a twofold dilution in the assays that are used for flu. But we do know that for flu, that the various neutralization assays and the HI assay, a twofold dilution is about the same. And we can also pretty much guess that it's not unreasonable to match these up by twofold, at least approximately for SARS-2. Because indeed, with the Omicron viruses, that's when we really get the breakthroughs, even for people that have high titers against the vaccine breakthroughs, have high titers against the original virus. There are also immunodominance effects here that are in both systems. Very similar type of effects. I'm not going to go into the details of them, so I can get into other stuff. The next bit of other stuff is to look at where the amino acid substitutions are that cause the major antigenic change that is responsible, that's seen by these assays. This is the flu trimer with the antigenic sites, the 130 odd, I think, amino acid locations colored on the left-hand panel for the different antigenic sites. And on the right-hand panel, the receptor binding site in yellow, and in the green and brown around that, the amino acid substitutions that are typically the ones that cause the major antigenic change. So very much the antigenic change focused by substitutions very close to the receptor binding site. We see a similar thing for SARS-2. This is the SARS-2 ACE binding site on the right in yellow. The figure on the left is a zoom in of the same one that we were just looking at for flu H3 by Bjorn Koladal in Ron's laboratory. And again, the substitutions in red here are the substitutions that have been causing the major antigenic change in SARS-2, and you can see that most of those are also very close to the receptor binding site. We've also seen at this meeting that on the fluke side from Ron Fouché that this is also the case for the B viruses, Mathieu Richard for the H5, from Joachim and Daniel for the H9 as a poster, also Mathilde as a poster, and previously Bjorn for the flu Bs and the H1s, and the H5s played 2.1, Nicole Lewis for the equine strains, and also Nicola and Amy for swine flu. So this is also, it seems, a very similar pattern between the two systems. And of course, that's, yes, the other thing about the two systems is that almost all of the amino acid substitutions that are taken in nature that are fixed, and also most of the ones that are explored as well, the vast majority, are also caused by, their amino acid changes caused by single nucleotide substitutions. One of the reasons why I mention this is because this massively reduces, if one is really just focusing in the region of the receptor binding site, this massively reduces the area that one needs to explore computationally and experimentally to figure out what might the virus do next, or what advantage might one virus have over another that are extant circulating, and trying to estimate which might take over. But there are differences between the evolutionary processes as well, as we know that in flu, in terms of the antigenic phenotype, and that's what I will focus on here, it's almost always this incremental accumulation of amino acid substitutions, some of which are antigenic, and these are being selected for by immunity in the population, and these substitutions close to receptor binding. For SARS-2, hasn't been so obvious that that's been going on. Right? I mean, if you think about this antigenic map here, you know, there's not much antigenic difference at all between the wave 1 virus and alpha. So this is almost certainly not due to an immune escape, of course, as we all know. And similarly for delta, not much of immune escape either. More of immune escape for these variants that have 484, and of course for the Omicrons as well. But there is incremental accumulation of amino acid substitutions, and they do cause antigenic change in the interests of time. And here are some, for example, with the 484K version of alpha, antigenic change indicated by the top arrow here. The B1526 with 484K, the antigenic change there. And then among the delta viruses with 484Q. And these typically increase over time. We've actually got data for that I was going to show, but in the interest of time, I'm going to skip over it. And when immunity gets higher, these antigenic escape substitutions come up. But of course, that's not how alpha appeared, or delta appeared, or Omicron appeared. We don't know for sure. But the best hypotheses, certainly for Omicron, are the evolution in chronically infected individuals and then getting out into humans. So the Omicrons, and this great example, and a number of laboratories that are studying chronically infected individuals. I point out just one here by the Mount Sinai folks, in particular data that with multiple, but that I hear about through Viviana Simon and Han van Berkel, with the B123 virus, showing that indeed there are chronically infected individuals that can transmit on variants that have a bunch of substitutions. But let's take a look at that. I mean, we know that Omicron is it in, I think just in spike, it's, I forget now, something like 15 or 17 amino acid substitutions, but we see that the antigenic difference is really not that big. In fact, the antigenic difference is kind of what we would expect if we were just looking for, if we were just expecting what we would see in flu. I showed here that about the same amount of gap. And one of the things that is going on here what we've done is to mark some different regions of the SARS-2 antigenic map, mark amino acid substitutions that appear to be sometimes experimentally tested as well to be predominantly responsible for these regions. And for the SARS-2 here, among all of these spike substitutions and the RBD ones in gold, and this is great data, of course, from Jesse Bloom's laboratory on this. These are these substitutions that we've marked here are those from David Ho's laboratory, with about 6 substitutions when put in individually in wave 1 virus cause substantial antigenic change. But in terms of class 2 antibodies, which the human vaccine data is immunodominant to, just these couple of amino acid substitutions. So although there is this process, likely in these immunocompromised, chronically infected individuals, we've still got a relatively small amount of amino acid substitutions, although this is different, of course, from the mechanisms that we see in flu. The other thing that we see in SARS-2 is the recombination. This has happened, this has circulated, this stuff has not persisted longer than a few months, at least not the stuff that we get to see, of course, in the great work by Annie Sloan's laboratory about how reassortment is happening all the time for flu. We just don't get to see it unless there's tags in there. So we really don't know how much recombination is going on. But the recombination, where there's major, easily detectable recombinants, that's clearly happening, but not yet persisting. The other thing that is happening a lot for SARS-2, which is very similar for flu, is a whole bunch of parallel evolution. Here we're looking at, actually I'll go to this figure first. Here we're looking at amino acid position 484 that we're all very familiar with. It's a phylogenetic tree here in gray on the left of the viruses up to pretty much the end of Delta and before Omicron. And each of the dark blue dots in here is a different occurrence of 484, either in this region, in the alpha viruses, or in this region in the delta. And you can see that it's happening all over the place, and it turns out that this is actually convergence is a great computational estimator of which strains are being selected for in the human population and which ones are more likely to emerge. And the orange dots here are the 484A that is seen in Omicron. Just briefly, this is work by Sam Turner in Cambridge, looking at how much convergence there is in the different substitutions, for the different substitutions. On the right here is more convergence, and here you see marked all of the substitutions that have been seen in Vogt-Voice, and you see that many of them have high convergence scores. And if we remove the substitutions that have been in Vogt-Voice but are not antigenic in them, you see almost all of them have these high convergence scores. Similar sort of thing in flu, I'm not going to go into. So, there's a bunch of computational ways that one can estimate what is being selected for. Of course, tying this up with experimental work is really essential. Great work shown yesterday by Francis Walsh from the Bloom laboratory. Similar work happening in other laboratories, in Wendy's laboratory, and a great laboratory in China with really high throughput on this. Super work in Gabi and Yoshi's laboratory, doing this for flu from years ago as well, and still very much today. And increasingly looking at this in high throughput methods in Ron Fouché's laboratory, similar also to the stuff that Francis talked about yesterday. It turns out that one of the things that happens in flu is that when somebody gets vaccinated, I'm going to look at this bottom figure here, not only do they get immunity with the strain that they're vaccinated against, on the y-axis here is immunity in humans, and on the x-axis is basically antigenic evolution over time. These individuals were vaccinated here. They don't just get immunity here, but they get immunity that is boosted against all their prior immunity as well. We take advantage of this in the flu world. There have been lots of studies in this in many humans, and there have been 3 updates of the flu vaccine strain in the last few years that have taken advantage of this back boost to protect against newly emerging clusters and also against previous clusters. It's very robust and for protection as well. We didn't know whether or not this was going to be the case for SARS-2, but it is also the case for SARS-2. These are some data from the COVAIL study with different vaccinating with different arms, and we see just as much of a boost against the original viruses when vaccinating with the prototype as with vaccinating with BA1. Really great work led by the folks at NIH. Chris Rippert's among them, who is here today. Finally, what I'm going to do is I'm going to talk about what we think is a pragmatic approach for using computational and experimental and best computational experimental combined estimates for improving vaccine strain selection with this protocol, which we have proposed for flu. We're very much tied in with Dave Wentworth on this for how to advance the vaccine strain selection in flu, and the link at the bottom for a document that Wendy Barkley, Paul Callan, Ron Fouché, and myself did for the UK government for medium and long-term vaccine strain selection for SARS-2. Step 1, quantify the existing population immunity. This is stuff that, as we talked about in the antigenic evolution breakout on Saturday. This immune surveillance is something that is done some by the WHO system, but there's a great deal more that can be done because, of course, this is still a selection pressure on the virus. Step 2, predict, computationally experimentally combine, where the currently circulating viruses might evolve to in the future through a combination of surveillance and looking at rare variants like was shown with the parallel evolution, and also with experimental and computational prediction methods. This is the area that we need to protect, and by quantifying the existing population immunity, we can check to see where does immunity need to build up, but how do we build up immunity there? It's the obvious thing to do is to vaccinate in that region, but that's not what's going to protect. What's going to protect is not the strain that we put in, but the immunity that we get afterwards. And because of all that prior immunity, it's not necessarily the optimal thing to do to vaccinate in exactly the pace where we need the most immunity when there's a bunch of prior immunity. This is still a process that we don't completely know how to optimize, so we propose here to select a small number of candidate updates and to test them in small-scale serological endpoint trials. The COVAIL trial being an excellent example of that NIH has led. Then determine the responses against, for each of these different candidates, against what is circulating and thought to might circulate, and then to use these data to inform the optimal choice of vaccine strain selection, all prior to the strain selection process. The fact that this is being done for SARS-2, one imagines it's also something that sort of behind the scenes strategizing to make happen for flu as well. And importantly, to close the loop, to evaluate the choices, to evaluate what has actually happened, and to hunt for mechanisms as to why it's happened in some systems, why it hasn't in the other, and to make this whole thing more predictable, not only in terms of the antigenic evolution, but predictable in terms of how the immunity will change over time, and to perhaps get away from needing to do the small-scale serological endpoint trials, depending on how much extra understanding there is. I think that I've acknowledged folks as I've gone along well enough, but other than to say that the flu work has for many years now, for 20 years, been in very close collaboration with Kuan-Fu's laboratory, and for about 15 years in addition, our laboratory is also very closely hooked up with Gabby and Yoshi's laboratory in Madison. Thank you.
In the interest of time, we might hold questions until the discussion, and we'll move to our final talk of this session. So this one's happening virtually, and it's Leo Poon from the University of Hong Kong, and he'll be presenting on transmission of SARS-CoV-2 Delta variant from pet hamsters to humans, leading to onward human-to-human transmission.
Right, so can you hear me?
Yes.
All right, great. So thanks for giving us the opportunity to share some of our SARS-CoV epidemiological study, molecular ones, actually conducted in Hong Kong. Right, now to begin with, maybe I just give you an overview or background about the Hong Kong control measures of SARS-CoV-2 in the last 2 years. So basically in 2020, 2021, Hong Kong tried to use elimination strategies to control COVID-19. So that is, there's a lot of control measures, stringent ones, to control the circulation of this virus in the community. So basically universal mask wearing, active contact tracings, aggressive control measures, testing, even basically we test a lot of manholes within the city to try to identify asymptomatic patients. And it worked quite well. And then because after that, within these last 2 years, 2020 and 2021, only 2% of the Hong Kong population get infected. So basically, many of us in the last year actually are naive to COVID-19, right? Of course, and we have tried to be have a very stringent control measures in controlling travelers. That is the reason why, many of us, the members in Hong Kong, cannot attend this meeting physically. But with that, so basically we can manage to put a lot of our resources to try to study a lot of the COVID cases in Hong Kong, and we actually sequenced about 25% of the Hong Kong cases from 2020 to 2021. And we can manage to identify several interesting transmissions. Like for example, we managed to identify infant transmissions right at the beginning, and then we also identified reverse zoonosis from human to dog in 2020. And we also managed to identify cases that have been reinfected by COVID-19, right? And also we managed to try to track the importation of these variants very closely in the last 4th wave, right? We went to wave 5, wave 4. We know where did they come from, and then we know how does it actually transmit. Basically, we know that they are being transmitted sometimes in hotel, and then subsequently spread to the community. And we also managed to use this molecular epidemiology to understand some of the super spreading event, to try to explain why this virus or this particular variant have been spread into our community. But most important of all, we managed to use this data to try to inform our policymakers so that they can try to adjust their control measures to try to suppress the COVID-19 circulation in Hong Kong. So with this, actually we have been doing quite well in 2020 and 2021. After May 2021, we basically hardly have any local cases in Hong Kong. You can see these at the right side. Most of the bars actually in blue. That means that they are all imported cases. So we have a very peaceful time starting from May last year to December last year. And in fact, we managed to try to track quite a lot, about 25% of the incoming travelers, and to try to study their variants that have been infected. And we managed to, basically in short, we managed to demonstrate that travel hubs like airport can be a useful central site to monitor SARS-CoV-2 sequence variations or sequence diversity in the regions. Right, for example, we can able to identify COVID-19 Omicron variants in mid-November last year. Right, at that time, we know that in mid-November there were upsurge of a B1.1 529, basically Omicron, in South Africa. And within the same time, we identified cases in Hong Kong. Basically, these are imported traveler, and they cause hotel transmissions in one of the quarantine hotel. And they are all, and we confirmed that these are vaccine breakthrough cases. And most important of all, we managed to identify this variant very early. We basically identified this case in 22nd November, and then we managed to tell these results to our government 3 days after. But what I'm saying is that we have been doing very hard to try to understand the phylogenetics or variants that keep coming into Hong Kong. Right, and then with this background, we can use these viruses like the Omicron isolate to try to characterize them. Like for example, Michael Chan's lab tried to use the Omicron BA1 isolate to characterize it in his ex vivo systems, and Mark's team managed to try to use this Omicron variant to try to understand the neutralization antibodies level in individuals vaccinated with different type of vaccines. Right. So in 2020, we ended up in a very different story because we have multiple introductions of BA1, BA2.2, and so on and so forth. Even we found recombinant virus in our imported travelers, and which I'm not going to talk about it, but I would like to basically try to talk about the Delta variant that we were able to identify in our local cases, and it was imported by, in fact, the hamster. Right now, first of all, the whole story started on 16 January 2020. Right, at that time, there was a pet shop worker test positive for L452R, basically the marker for Delta variants. At that time, we were actually puzzling because we don't know where these patients actually get the Delta VOC, because we didn't find any circulation of Delta variants for weeks at that time. But the job duties, basically, she is a pet shop worker, and that actually become the trigger because right at the beginning of this pandemic, we know that basically our lab pooling managed to show that hamster is a good model for studying COVID-19 or SARS-CoV-2 transmissions. And this basically pulled the trigger, and we immediately worked with the Hong Kong government to try to conduct investigations in that particular pet shops and also in its corresponding warehouse. We test rabbit, guinea pig, chichinia, mouse collected from these settings, and they were all negative by RT-PCR assay. Right, but to our surprise, we found half of the serum hamster that we tested, and they were all positive for SARS-CoV-2, either by serology or by RT-PCR assay, right? And by contrast, when we test similar number of samples from draft hamster, they were all negative. So suggesting that, right, hamster serum one seems to be the source of these Omicron or Delta variants that leading to human infections. And in fact, we subsequently confirmed this case. But before that, I would like to just basically give you the timeline about how does it happen. So this chart table shows you the index case that we have identified from the pet shops, and then we also screen for the pet shop A and then also the warehouse in the following days. When we do the follow-up investigations, we know that on 7th of January 2022, there was importation of multiple pet animals, about 1,000 animals from Europe. And among these, about 118, they were serum hamsters, right? And then on that particular day, when they arrived in the warehouse, some of these hamsters had already transferred to multiple pet shops, including the pet shop A. And later on, that's basically a few days later, we identified a family cluster. They were all infected by the Delta variant. And we know that these are father, mother, daughter, and son. Right, and then we also know that father, mother, and the daughter actually visited the same pet shop A, on 8th of January. So basically, one day after these hamsters arrived at these pet shops. So there's a good epidemiological link about this hamster and this cluster. Now the next question is whether this family cluster acquired the infection via the index case or not. And we believe this is not the case because when we do the phylogenetic analysis of these SARS-CoV-2 genomes from the patients and also from the pet shop hamster, they were different, right? Basically, we know that the father of the hamster cluster, the family cluster here, mother, father, and son, genetically, their virus is genetically very different from the index case, as shown here. By contrast, this case, the human one, the index one, the sequence is basically very similar to several hamster samples, and this family cluster have sequence similar to this hamster sample coming from a warehouse, right? And we know that subsequently, this family cluster spread the disease to their friends and relatives, and in fact, this virus keeps on spreading in the community for about several weeks. At the end, there are about 100 cases identified in the community, and these are the phylogenetic tree of these cases. Now, those highlighted in green, these are hamster sequence. Right? You can see that genetically they are different. And some of them are clustered to human cases, and some of them are here and here. Right? But there's a human cluster here, which we don't know where this patient acquired the infection. Probably that may be some hamster which have the Delta variants, but we missed them in our early investigations. In fact, this seems to be the case because when we try to test other pet shops, at least two of these pet shops, pet shop B and C, they have evidence to show positive cases, RT-PCR. And then subsequently, the government actually have a recall of all these hamsters that were purchased at that period of time. And at least one pet hamster, surrendered one, from the pet owner, test positive for COVID-19, right? So multiple evidence suggested that the virus actually originated coming from Europe, and then they traveled to Hong Kong, and then they arrived in the pet shop. And this caused multiple transmissions to different individuals, and then these individuals spread the disease within the community. At the end, there were about 100 cases that we found in Hong Kong. Right, and then the implication of this study is this hamster, although experimentally we can infect them, in natural setting, these hamsters can still infect by SARS-CoV-2. And then also, hamster can be served as a secondary reservoir for SARS-CoV-2. We know that the virus can still transmit between them. And then the virus that actually circulates in hamster can still transmissible to human cases. And then in this case, we found sustainable human-to-human transmission as well. Right? And this study also highlights that animal trading or movement may facilitate SARS-CoV-2 spreading across countries. Now, you may ask me whether there's any signature markers for this particular Delta variant. We found two signature markers, L85F in spike, and also B427G in the receptor binding domain. But when we look at this, we don't see any special features or they're changing any adhesiogenicity or receptor binding. We really don't see there's any evidence to show that they had altered the phenotype of this virus. And in fact, when we check these mutations in all the human cases, they are preserved. So suggesting that these are not adaptation in hamster. Right? Of course, let's not forget about the other animal viruses, right? We know that SARS-CoV-2 can infect a mink and also infect white-tailed deer. I'm looking forward to hear the talk from Andy next, because I really want to understand the situation about COVID-19 in white-tailed deer in US. Right, okay, now I'm going to switch a topic, which is I'm going to talk about some unpublished data. Right, Earlier this year, we basically demonstrated that the transmission bottleneck of SARS-CoV-2 is quite narrow, which basically, our finding agree with those generated from other groups as well. So basically, the bottleneck is extremely narrow. We are talking about a few variants, right? That means transmission of low-frequency SNPs between hosts is very rare. So with that understanding, we can basically say that most of the variants that we detected in a single sample, most of these variations may be de novo mutations. All right. Now, with this understanding, we basically try to ask two questions. First, do different variants will generate different, or will have different ability to generate sequence variations? And secondly, would the vaccinations to the host will affect these virus will induce, or whether it's going to induce or suppress the generation of minor variants? So to answer these questions, we analyzed a couple of samples from who were infected by VOCs, Alpha, Delta, and Omicron, and then also VOC, non-VOC from it, which coming from Hong Kong, right, coming from wave 3 and wave 4. And then among these individuals, some of them are vaccinated with mRNA vaccines and inactivated vaccines, or they have not been vaccinated. So these are the two criteria. I don't have time to talk about it in details, but basically we managed to do deep sequencing among these samples. To cut the story short, we found that VOC seems to have a more ability to generate sequence variations, and these are the number of intra-host sequence nucleotide variants amongst VOC and non-VOC. So we found that VOC seems to generate more SNPs than non-VOC. And we measured the sequence diversity. Again, we have the same conclusions. So VOC seems to be able to generate more sequence variation than the non-VOC. All right. So that seems to have some differences between different variants in terms of their ability to generate sequence variations. And how about the vaccinations? So we do a similar analysis. For the Omicron one, we didn't find any effect about the vaccination, no matter whether they are vaccinated with mRNA, inactivated vaccines, or unvaccinated. We don't see there any difference between the number of SNPs and the sequence diversity among these samples. However, when we look at the Delta variants, right, we found that there are some signals in between these two. Those vaccinated with mRNA vaccines and those which are unvaccinated. There is a significant difference between these two groups. But this difference seems to be very small because when we measure the sequence diversity, we didn't find any significance, right? So we don't know why we found this in Delta but not in Omicron. So we speculated that maybe these people have a different post-vaccination time when they were infected, or maybe the variant itself have intrinsic differences between Delta and Omicron. Or maybe the vaccine itself have a different ability to select mutation between Omicron and Delta, right? But I would like to highlight that although we found there may be some differences in terms of number of SNPs, many of these actually are silent mutations. We didn't see any increase of the non-silent mutation in this group, in the Delta group. So most of these mutations actually are silent mutation. When we actually calculate the ds-DNA ratio, we found there's actually vaccination can enhance purifying selections that make the virus less likely to be mutated. And we also studied the mutations, protein sequence among these groups, and we didn't see there's any signal at all. So we didn't find any vaccination can select mutations. We also tried to map the SNPs according to the antigenic site and also HLA restricted T cell epitopes. And again, we didn't find any effect about the vaccination on these sequence variations. So the conclusion is we didn't find vaccination can induce more mutations in the vaccinated individuals. Right, so this is my summary. So I demonstrated that to use NGS to try to conduct molecular surveillance of SARS-CoV-2 in Hong Kong. Right, and then we also managed to identify hamster can be infected by SARS-CoV-2 in natural settings, and in fact, that could be a bidirectional virus flow between animal and human interface, right? But the next question actually is something that we cannot answer, is whether these animal, the infected ones, can generate novel variants that may jeopardize human health. This is something that we need to big long-term systematic studies to address these questions. And finally, use NGS to try to identify these minor SNPs in vaccinated individuals and also unvaccinated individuals. And we know that VOC seems to have a much stronger ability to generate mutations. That means that they are more likely to explore new sequence space. And by contrast, we didn't find any effect on vaccinations. We didn't see it can select for mutation that associate with immune evasions. Right, okay, so at the end, I would like to thank my colleagues in the School of Public Health HKU, and also CS, and the colleagues from St. Jude. And then I would also like to thank the other funding organizations and my colleagues in other institutions. At the end, I would like to thank you for your attention.
Thank you so much. Again, in the interest of time, we might move straight into our discussion. So if you join me in thanking all the speakers from today's session. And then we'll ask all the speakers to come join us up here on the podium, and we'll throw to the floor for any more questions. So I thought I might give you a brief summary of who spoke on what to kind of trigger what the talks were. So our first talk this morning was Sima, and she spoke on the pandemic potential of swine influenza. The next talk was Gabrielle, who spoke on co-infection of influenza viruses. The third talk was to Miranda, and she spoke on the hamster transmission. And then it was Jennifer, who spoke on exhaled breath aerosols. And then the final one before the break was Jamie, who spoke on the environmental stability of droplets. And then we came back from our break and we had Derek, who spoke on patterns in antigenic evolution. And then we've just heard from Leo, who spoke on pet hamsters and mutations within variants of concern. So we'll go to the floor for the first question.
I think Katja was first.
Oh, my
Mike. This is a question for Leo Poon. I don't know if he's still there.
Yes, you should.
Okay, great. I was really interested in your finding that VOCs within hosts generate more sequence variation compared to non-VOCs, and so I was wondering whether you could maybe speculate on why you think that might be the case. Is that distribution of mutational fitness effects may be different in VOCs versus non-VOCs, or do you think it has to do with kind of viral dynamics and how they differ, and kind of just mutational supply?
Well, actually, I mean, I don't have a direct answer. We believe there's an intrinsic difference between the ability to generate variants. In particular, I mean, you can see why Omicron or Delta seems to be diversified. I don't know whether it's because there's some mutation in the or variation in the RB polymerase, so that they may be able to generate more variants. This is something we didn't look at it yet, and we just managed to get this data done very recently. This is something that we want to do next. And in particular, I'm just really interested to look at the like BA2.2 and BA1, whether there are any difference, and see what is this phenotype associated with the fitness. Right, this is something that we would like to actually address. But sorry, I don't have a direct answer for this.
Great, thank you so much.
Hey, Leo, it's Mike Warby here. Another comment for you that I was just thinking about your work with the hamsters in light of we've just had a couple papers showing that the most likely scenario for the origin of the whole pandemic was a similar sort of situation that you've documented with the hamsters, where you have sustained contact between an infected animal host at the Huanan market and multiple host species jumps. And I just wanted to say that I think one of the really important things about your work is that it shows that it's actually not a weird thing that you would have multiple jumps, as we documented for lineage A and B, which we show are very, very likely to have been separate jumps from the animal reservoir. That when you have those conditions, it's actually almost inevitable that you'll have multiple jumps, as you've shown in hamsters, and Marion Koopmans has shown on single mink farms. You have sometimes up to 5 different individual humans being infected with viruses in separate transmission events. So any thoughts on that?
Right. I think this is something, I would say this is a science that we actually don't know if we don't actually look at it. The hamster that we have investigated, they are all look healthy, right? We didn't, we have a vet to actually try to check them. They are quite okay. So this type of science study seems to be common then, which this actually reiterate the importance of doing a systematic long-term surveillance study to try to check the baseline, and so that we know something went wrong. And in Hong Kong, we are fortunate because the cases, the COVID cases in Hong Kong is so low, so we can actually detect some unusual pattern, right? This is something that I think I would like to reiterate. Having a long-term systematic surveillance, no matter how small scale it is still better than doing none. Thank you.
Yeah, and I agree, and great that you captured that. Thanks.
Good morning. A lot of great talks, but this one's for Seema. You'd mentioned in your ferret transmission studies, you had some transmission by seroconversion, but no detectable virus by infectivity assay in the nasal washes. Have you seen that again in other studies? And if so, have you been able to identify RNA or in the lung maybe, or something like that, depending on the virus?
Yeah, no, this is a good point. So we have noticed this sporadically, where we sometimes have no infectious virus in the nasal lavages or nasal washes, but we do get seroconversion. And I think it's a combination of the fact that there is shedding only, not on sustained shedding for multiple days. So when you have prior immunity, you the duration of shedding is lower than in animals without prior immunity. That we've consistently shown in both experimental infection as well as in the recipients. The other thing is the way we do the wash, it's like a neti pot. So we're just getting things very superficial. We push liquid up one nostril and collect what comes out. So there could, of course, be replication both in the trachea, the nasal pharynx that we're not collecting, or in the lungs. We don't sacrifice the animals during active shedding to look at that. We use serology as sort of an indicator of that. So I don't think this means that it isn't being expelled, which is why we wanted to do the chain experiment. I actually thought we would be able to get at this whether there's like asymptomatic transmission of an animal that has low levels that could eventually forward transmit, but we're going to try to get back to that.
Thank you.
Yeah.
I guess that's a really good segue then to this question, to link with Tamarind and Jennifer from Don Milton's 2 talks. So we could actually see emerging immunity at the time of transmission. So if you did the onward transmission experiment later than day 3, such as day 5, we might have emerging immunity. Would that impact the ability to transmit, such that when you said that N antibodies were emerging in the people, were positive in people that were then virus shedding, could that actually be due to response to their active infection, if that can come together?
Okay, I'm very sorry. There is a bit of an echo, and I am having a lot of trouble hearing your question.
Yep. So Jennifer, when you said that the vaccinated people maybe had prior infection and so their N antibodies meant that they weren't actually infectious at that time point, could it actually be that they're currently controlling their current infection, so they're seroconverting early rather than being prior infected?
Yeah, that is also a possibility. We were seeing people at a range of post-symptom onset points, so it is possible that someone was having an immune response to their active infection at that time. So I didn't really go into it in the talk just for time constraints, but that is something we had considered.
And with those time points, then maybe inform the hamster experiment, so you could say when the secondary transmission experiment could be. So this is now for Tamarind, jumping back to hamster.
I'm not sure we would need to push it longer because we're looking for 100% transmission, which we were able to see. Technically, we were able to see that 2 days post the contact 1 exposure. It just wasn't in all the compartments that we looked at, but we can see that in our day 3. Now, if that's going to be the same for all variants, that could change. Obviously, we know that Omicron has different kinetics in cell culture, but also in hamster. So it potentially could need to have later exposure if we were ever able to get transmission to occur in the hamster.
I think at the end you said you wanted to get at correlates of protection, so could there be correlates of protection that might protect from onward transmission? Might be the time point.
We might do a question from the chat and then we'll go back to the floor. So this is for Gabrielle. It says the lack of co-infection in vivo might explain why you don't see the beneficial effect in vivo, but would it explain the suppression effect that you observe? Or is there something else going on that makes a suppressive effect inherent to the co-infection?
Yeah, I think there are a lot of things that are happening in vivo that could create the suppressive effect. So one of the things that we were kind of postulating is that it's the availability perhaps of cells that could be infected. So if you can imagine the respiratory tract, it's not like a cell culture dish where the virus has the ability to freely move around the virus medium, but rather in that spatial structure, it's much more restricted, like with the mucosal, with mucosa, the membranes, and etc. So it likely could be just a lower prevalence of co-infection. As well, we're going in with very, very low doses of the virus, so we're definitely not saturating the system and really pushing the possibility of co-infection.
Yeah, this is a general question for any of the transmission talks. We know that during these times, the use of masks and the mitigation things that they were done reduced very much transmission of influenza. But apparently that was not the case for rhinovirus. And I wonder what are the thoughts about why rhinovirus were not stopping. It's because they transmit better by formalities. I mean, it's a non-enveloped virus, but it's also respiratory. Is transmission different? Is that they are able to go through masks? Or what are your thoughts?
I think that's a fantastic question, and I apologize, I'll take it first and then I'll pass it on to anyone else who wants to comment. So I think what we don't understand, Adolfo, is how other respiratory viruses transmit. I think that was highlighted to us during the COVID-19 pandemic, right, where we clearly have a virus that transmits through clusters rather than a sort of stochastic transmission that we normally see with flu. What we don't understand for rhinovirus, say, is how that virus transmits. Perhaps it is fomite, that it is persistent in the environment for longer periods of time, or that it just lasts in some other way, or it's infecting in some other way. The dose, the modes, the behaviors that influence transmission, we have no idea. So maybe it's a long answer to say we don't know.
I would also add, we think the limiting forget the name. But we only think that there's a few particles that are required for transmission to occur. And so when you have such a low barrier, it's a lot easier to have transmission and a transmission event occur, regardless if you're wearing a mask or not, although we do know that it does help prevent some.
And I'll finally just add a comment that we had a paper earlier this year where we actually did measure aerosol shedding with masks and without masks. And this was still in the era when people were wearing cloth masks and not N95s and KN95s. And we did see a reduction. We did get a couple of instances where people were shedding even while wearing a mask. So I know we're not directly transmission as some of the other presenters are, but if you use aerosol shedding as sort of a proxy for transmission, then we do see a reduction when you wear a good, tight-fitting mask. We do have a question.
Hi, this is a question for Derek. I was interested in your slide on the, I think it was like protocol for immunity management, and in which you laid out how we could potentially improve our vaccine selection, strain selection. And one of the things you said was to improve protection. I'd just like to ask you, like, to clarify, what do you mean by improving protection? Does that mean like increasing the vaccine efficacy, or reducing hospitalization, or do you mean by reduced transmission in the community? Because now we know that even with matching strains, you still can get shedding and you can still detect virus, or you can still be infected. So just want to like ask you, what do you mean protection in this context?
Yeah, thank you. You had very good layers of subtlety to my very coarse statement, and what I was actually talking about, because of what we would be optimizing in the easiest way with serological endpoint trials, is just antibody titers measured by probably HIs, maybe some neutralization assay in the area where the viruses actually end up circulating. I understand, and that's why I say I think it's very good, your commentary, which is a much more subtle interpretation based on what I said. I mean, in general, it's got to be a better thing, though, to have higher titers in against the viruses that you're exposed to. But I agree, it's absolutely not the whole story. And I forgot to acknowledge Ian Barr's laboratory for many years.
On that, we might bring our discussion to a close. If you'll join me one more time in just thanking our speakers and the. So I believe we're moving straight into our next session, so we'll hand over to the chairs from Emory.
Great. Okay. Great. So this is session 4, human-animal interface and animal surveillance. And I'm Troy Sutton, and this is Lucas Ferrari, and we're moderating the session. We want to point out that the Emory series has a Ferrari, not a Miata. Sorry, this is Andy Bowman, and he's going to be talking about. Great, thank you. I think our talk here on white-tailed deer is going to be a nice example of how we were putting the band back together to show the pivotability of the CEIRR network. And so as we look at the establishment of SARS-CoV-2 in an animal reservoir, we've heard and we all know it's a flu network, right? The potential detriment of having a natural animal reservoir for a human pathogen. So we'll quickly run through this. Maybe. Okay, so almost a year ago, we had the first report of SARS-CoV-2 detected in white-tailed deer, in free-ranging white-tailed deer, and so There had been a series of work leading up to that showing some seroconversion in free-ranging white-tailed deer, experimental studies showing susceptibility. And so as part of a kind of pilot project we had going at Ohio State, we were out there flipping rocks, sampling anything we could get our hands on, and white-tailed deer was a group of that. And in all reality, it had been a very boring project, and I was ready to pull the plug until we got to this group of white-tailed deer, and we hit a bunch of positives. Initial report comes out August 2021. Ultimately, our paper comes out later in the year detailing all of that work. So just a quick overview of that. This was a very small sampling, about in a very small contained network in Ohio, in Northeast Ohio, where we were able to get our hands on some cull deer. So these were deer that were removed as part of a deer management program in some urban park settings. We had surveillance occurring at 9 sites, and we had very high infection rates in those deer. As you can see in the graph, right, we've got upwards of probably close to 70% positive in some of those sites, which really got us questioning what was going on in the deer. And through all that work, right, we realized that not only did we just have positives, but we had some repeated sampling, and we were able to find some evidence of deer-to-deer transmission. Not only did we have deer-to-deer transmission occurring, but we also had multiple introductions, essentially one introduction per sampling site, which really got us, wondering what's going on. This is a very small sampling that we had, and so as we got these results, the question was, how are we going to answer explore this a little bit further and take it beyond this small kind of park network that we had been doing our work in. So we expanded it across the state of Ohio. The goal really was trying to understand, is this some weird phenomenon of this park system and these urban deer? Do we see it in more deer? There's roughly 30 million deer in the U.S., and so the idea of, do we see spread beyond this? What's really happening elsewhere? And then wanted to answer questions around persistence, spatial spread, and evolution. So our first real opportunity to do any sort of look in those deer came as hunting season of 2021 and continues into winter 2022 came about, and then we had partnerships with the Ohio Department of Natural Resources, USDA Wildlife Services, various metro parks, basically any place we could get our hands on deer. We used the kind of the divisions of the state that the Department of Natural Resources uses, and it's shown in the map, so that we tried to spread our sampling efforts across the state as uniformly as we could to really get a wider expansion of what's going on in the deer of the state. So overall, we end up getting 1,500 deer samples. We represented 83 of the 88 counties, and so we felt pretty proud of ourselves that we were able to get out there and actually represent most of what was going on. Of the breakdown of that, we had 713 hunter-harvested deer, and so typical hunting deer were then brought into processors or check stations where we were able to get nasal swabs from those deer. Those were representing 81 of the counties, and those are primarily the rural deer. And then we have another 801 culled deer, and so these are deer that were taken as part of management programs, sharpshooting events that were occurring to control deer populations, especially in urban settings. And so those end up representing our urban deer, and then a handful of other deer that we just can't help ourselves when you see a deer carcass along the road and you need to swab it. So that makes up the rest of those. So what's it look like? Overall, 10% positive, and so different than our initial 35% positive that we found in our first report, the urban metro parks across the state. We're moving into a lower prevalence, which might suggest we're moving towards maybe a more established reservoir. As we look across the map there, the sizes are showing the sampling intensity, so size of the circle is how many samples we're getting. And then color scale, the green is low prevalence and red is high prevalence. And so you can see we've kind of got a gradient across the state. The gray shaded counties are the urban counties, at least as classified by USDA. And so as we look across, with the distribution of things, rural deer certainly had increased odds of testing positive compared to those urban deer. And then male deer, which we'd seen in our first survey, also had increased odds. And we think that has to do with movement. As you look at the timeline distribution of our sampling, obviously it's very heavily focused on November, which is when we have primary hunting season in Ohio. Gun season occurs in November, and so that's where a lot of our samples came from. But then we had some of those ongoing deer management programs that continue a little bit longer into the winter, and so we continue to get samples through that time period. So, getting to the meat of it, we have 80 of those that we are able to sequence. That represents 34 counties. And as we look across this, most of what we saw were delta, and so we have multiple delta introductions. So across that time period, we detect about 30 different delta introductions across the state of Ohio, representing 12 different delta lineages. Some of those we certainly have clusters that seem to represent onward deer-to-deer transmission. The rest of them, though, we get this interesting detection of alphas. So 2 different clusters of alphas that represent 2 different introductions. As you look at the figure, you can potentially see that our initial study deer here kind of have that red highlight on the circle. These are not onward transmissions from those deer. These are different introductions that have occurred since then. They're also not related to the mink detections that we had across various mink farms in the U.S., and they also do not seem to be progeny of other white-tailed deer viruses that have been detected in the U.S. at the time as well. So truly separate introductions that have occurred into the Ohio deer, and we really don't have evidence of state-to-state spread. So as we talk about all those different delta lineages that we picked up, the 12 different ones, they really do seem to be tied to what's in the people as what's ending up in the deer. And so across the x-axis, we have the lineages that we're finding in humans, and so this is sequence data we took from the Ohio Department of Health and looked at what they were finding in the people at the same time we were doing surveillance. And then the y-axis has the number of sequences we're getting for white-tailed deer. You can see a very nice relationship there that what's more common in people ends up being more common in the deer, although we are detecting some rather rare lineages in the human population that are still spilling over into the deer, and we're picking them up. You can also see the number of introductions into the deer by the different lineages, and some of those include being identified in multiple counties. And then you can also look at the size of the deer cluster and how many we have in each of those. So really, right, the idea that deer are the sponge, they're picking up whatever's in the people, spilling over into them repeatedly. The rather interesting thing to us is especially thinking about the establishment of national reservoirs, these alphas. So those alphas, you can see in the purple dots at the bottom, we picked them up greater than 6 months since they were circulated in humans. Right? So we've got the idea that alpha had kind of died out in humans by that point in time. Certainly we're picking up a lot of delta, which is representing what's circulating in the people at the time, but those alphas really got the idea that the deer were able to maintain that for at least 6 months, which starts to question how much longer could they maintain those, and would other lineages also be able to be maintained. Ultimately, I think we're just short on time at this point. We haven't had enough time to continue to evaluate, and our sampling at this point is really limited to when the deer are being taken for either hunting or call purposes, and so we get this kind of yearly snapshot at them. We're going to have to really intensify our sampling efforts during those off seasons to figure out how those things are maintaining. As we look at the spatial transmission, we certainly have these clusters, and so you can take lineage by lineage and look at the clusters, and they're very geographically defined. Although some of them, as when you look at the AY103 in Northeast Ohio, right, we're covering quite a bit of ground with that cluster identified as A, and so certainly we have it moving through deer, transmitting through deer. Realize this might be skewed a little bit. It's by the centroid of the county, and so if you pull them all to the closest corners of the county, they may not be spread as much. But then you can also see other clusters like cluster B, which is in an urban park setting, and so you can see the transmission within that park setting where you have those clusters. If you look all the way over to the far side, we'll pick up the alphas, and so you can see maybe a little bit wider transmission, especially in those groups, in those viruses that had been in the deer for a longer period of time across southern Ohio. So those two clusters are shown there, and we've got a couple months apart where we're finding those viruses, and we know that those were at least 6 months since they were circulating in humans. So some sort of sustained transmission of the alphas, especially in southern Ohio, points us to we ought to be back there looking again for what's going on in that neck of the woods. Other thing to note is we have co-circulation, so if you put all those maps back on top of each other, especially in Washington County and Athens County, so two rather rural counties in Appalachia and Ohio, we have at least 4 different lineages co-circulating in 1 week, right? This is gun season, so we had heavy surveillance during that week, and we find at least those 4 different lineages co-circulating in the deer at one time. So certainly looks like those spillovers and then whatever transmission is happening within the deer population, right? There's an awful lot of SARS-CoV-2 in the deer, especially during that time. Everyone's asking about mutations and which mutations are we picking up in the deer. And so we do find some mutations in spike protein. Granted, these are fairly rare in some of the human data, but we are picking up a few mutations that we're really trying to understand, is that going to affect transmissibility back to humans? And then the idea of, right, what sort of long-term effect do we need to be watching for in the deer? To date, right, the deer really have not shown any clinical signs of disease, so they seem to be a pretty silent host that's transmitting virus. But obviously, if they're able to maintain virus, especially those that may be of increased risk to humans, it could present trouble for us in the future. So as we move through this pipeline, and this is really a great example of how to do the risk assessment pipeline. As we got those samples and found them positive, we sent them off to Richard Webby's lab, where he promptly pawned them off on post-doc of the day, right? And then we got some look at how we were able to have, or what sort of growth kinetics did we have of these. Everything seems to perform pretty much as we would expect. And then we also, in the TEPRS-2s, and then as we also look at the GAU3s, right, we've got some of those that are those deer lineage viruses that are certainly able to grow within those cell lines, and so some idea that yes, those could come back into humans, which really isn't surprising because we're not seeing a ton of adaptation into the deer at this point. Although, like I said, we're really limited on time to date. Some great work that John Franks did in Richard's lab also included some hamster work, and so as we were able to then inoculate some hamsters and look at the sera and how much neutralizing antibodies we were able to produce out of some of those deer isolates, you can see that we do have a little bit of lack of protection, especially against the Pfizer vaccinated hamster sera, and so that's in that AY118. But we also have a varying, some of the alphas, right, showing great cross protection against the deltas, which maybe isn't all that surprising. So no real smoking gun that we have, a major threat lurking in the deer to date, but we do have the idea that they are certainly able to hold on to and maintain some of those older lineage viruses that might end up coming back into humans at some point in time. So really questions of where do we go from here? How in the world are they getting infected? Everybody's got their leading hypotheses, including some very well-intentioned lady from California who wrote me a handwritten letter. Everyone's got ideas. Wastewater, contaminated garbage, some other hosts certainly are in there. I don't think direct transmission from infected humans directly to hand-feeding deer is accounting for all of these transmissions. So I think we've got something else. The proverbial window is wide open. We have no idea what it is. Question on how long SARS-CoV-2 can persist absent the spillovers from humans is a really interesting question. Maybe we could remove the absent from spillover because we have no idea how to prevent that at this point, but certainly some of those viruses are continuing to circulate, and so we've got to figure out how long they can persist in the deer population, and then what evolution will occur within that host. The long-term persistence in evolution, right, really is the big question, especially from the public health standpoint. I think most of the animal health side is not concerned about SARS-CoV-2 in the deer population from the animal health side. It's there, but not causing any disease. But from a potential reintroduction to humans, if we've got to look at it, there is the question about adaptation pathway to other animals. And so now, as we have white-tailed deer infected, will we see an adaptation into other host species that may further complicate future control of SARS-CoV-2? And then this looming question of what's the frequency of transmission back to humans. It comes up, especially during hunting season where we have higher contacts than we would normally have. But we also know that the animal-human interface, especially with people coming into contact with deer in lots of different settings, is really coming to light. And so I think we're probably heading down the path eventually of really trying to assess how frequently we have deer to human and human to deer transmission. So with that, I'm just the talking head. A lot of this work's been done by Martha and Richard's teams. Have to acknowledge the folks that we had helping us, especially get samples. It took an army, and then the folks in the lab, Dylan, Jacqueline, Deborah, and Heather are all here. If you want to know what really happened, you can talk to them. And other than that, I think I've got time for a question or two.
So I really like the work, Andy. That was fantastic. And I was curious, do you see any correlation when there is a spike in human cases in Ohio or in a county, and then when you're swabbing the deer as well? My pet favorite is wastewater for taking votes. So that's my vote.
So the reality is we really don't have enough longitudinal data to really look at trends, right, in waves and people. I think if I were designing a project, I certainly would want to have that, where we intensify sampling as we see a wave in people and see what that looks like. To date, right, we're not in that space, and as much as I'd love to be, we're going to have to shake the money tree pretty hard.
Hi, excellent talk. Thank you. So as you know, the time that you were sampling most of your deer, the hunting season, also corresponds to the breeding season for white-tailed deer when they're more likely to come together in larger groups. Have you considered doing any sampling at other times of year, understanding that that might be more difficult? And do you think that could give you any insight into the persistence in these populations?
Yeah, great point, right? And so that has certainly been one of our major hurdles at this point is our restriction to hunting season and when we can get our hands on the deer. Even if you look at our percent positivity over the months, right, there's a decreasing trend as we get away from hunting season, breeding season, and so that may very well play a role in it. Early on, we got some questions about whether the baiting used in the cull programs may be facilitating spread and give us an artificially high detection rate. We don't really see that, especially as we in our sampling have a higher positivity in the rural deer than we do in the urban deer. But I do think there is probably something to breeding, and I think that probably comes for the male, right? The increased odds in the males is they're moving and traveling and having more contact. So I think that probably plays a role there. But yeah, to look at real persistence, I really hate having to sit here and wait until the next hunting season to know do we still have alphas circulating in the deer or not. Right? We're going to have to close the gap somehow.
Florian, we are going to move to the next question. Sorry. I have the solution for his access problem. You can approach him. Thank you very much, Andy. So our next speaker is Gassi Kayali. He's going to talk about transmission routes of avian influenza viruses at the wild bird poultry human interface in Egypt.
Hi everyone. So if you were paying attention to yesterday's morning briefing by Richard Webby, I am the Ghazi, and I am the only weakness of the St. Jude's CEIRR program. But Richard forgets or to mention that everything I do wrong is actually from him because I was his postdoc. And everything good that I do, I learned from Ian Barr. Right? So, I work in Egypt. We have been doing human-animal interface studies over there since 2008. And today I'm going to talk on the projects that we have going on as part of CEIRR, but I'm also going to provide an update on the H5, H7, and H9 viruses that we've been seeing over the last few years. But to start, I'm going to give a brief introduction. How do I get this slide? There we go. So Egypt has been known to be a hotspot for avian influenza viruses. It seems that any avian flu that gets into the country likes it so much and stays there. So we started working there in 2008, right at the time when H5N1 clade 2.2 viruses were taking hold in the poultry populations over there and becoming pretty much enzootic. And we monitored these viruses between the periods 2008 up to 2014, where they really got hold, causing a lot of outbreaks in the chickens and also a lot of human cases. So in context, Egypt is the country that reports most of the human infections with H5N1 viruses. During that time, the strategy that the country was using was resorting to vaccinations in the poultry, and that actually caused more problems than being a solution, because we started seeing vaccine escape mutants in the H5N1 viruses, so that complicated the situation. In 2011, H9N2 arrived in the country. We started picking that up, and again, it started causing some outbreaks, but eventually, just like H5N1, clade 2.2 viruses, it got hold within the poultry population and also became endemic. So that continued to be the situation, co-circulation and co-infection between clade 2.2 H5N1s and H9N2s all the way up to 2016, when we started seeing H5N8, 2344 viruses coming in. We detected them in the wild birds, and eventually they also spread to the poultry, causing outbreaks. But so far, we haven't had them establishing themselves as enzootic yet. But when we had a period when the three viruses were co-circulating, so we had H5N1, we had H5N8, and we had H9N2. But eventually, we believe that the H9N2 and the H5N8 kind of pushed the clade 2.2 viruses out, and we haven't been seeing them since 2016 or 2017. So our surveillance focuses on not only the domestic poultry, but we also do some studies within the wild bird populations. And in there, we definitely, like any other place, we see a wider diversity and variety of avian influenza viruses, and we detect several subtypes. What we like to do is we don't only focus on the birds, we actually do human-animal interface studies. So a lot of our attention goes to the humans who are really exposed to these birds. So we always have a human component to our work. We always have a human cohort that is composed of people who are exposed to poultry, all wild birds, and we try to study what goes on in the human populations. So we did studies that we estimated the seroprevalence of H5N1 and H9N2 viruses in the humans, and then we did another cohort in which we estimated incidence, and we realized that we see, or we have a lot of cases and a lot more burden on the human side than what is actually known, or what the surveillance systems actually do pick up. And throughout our studies, we always came back to see or note that live bird markets are really problematic for both public health and animal health. And that's why for CEIRR, we decided to focus on live bird markets. So our goal was to understand really the routes of transmission between animals and from animals to humans in that live bird market setting. So we designed a 7-year prospective cohort study in markets in the northern side of Egypt, which is right there on the Mediterranean. What's unique over there is that migratory birds, there are lakes over there, so migratory birds could come and stop. What happens then is that some of these birds are trapped and then taken back to the live bird markets and sold live for food. But in that same market, you definitely have the vendors who sell domestic poultry, so you have domestic chickens and domestic ducks, and of course, you have the humans. So we had a unique niche in which we had a wild bird, poultry, human interface. So we plan to enroll about 1,200 market workers, and then every time we go and sample, we're going to be sampling both the wild birds that are there, the poultry, and also the environment. From the humans, we're collecting nasal swabs, we're also collecting hand wipes, and we're obtaining sera From the birds, we get cloacal and oral swabs, and from the environment, we get wipes from surfaces, we sample air, and we sample water that is being used for drinking for the birds. And the samples that we collect, we initially start with trying to find out whether we have influenza in samples by RT-PCR. So the cohort is fairly new, and we've been enrolling only since November of last year because there was time that was lost between obtaining contracts and then obtaining all the paperwork that is necessary for a human cohort to happen. But since then, or between November 2021 and last June, we have obtained a little bit over 1,600 samples. So if you look by species, among the wild birds, our positivity rate is about 7%, while in the poultry it's up to 23%, so fairly high for a surveillance program. But because it's a live bird market, I think that's common. What we used to see is about 5% positivity rate, but because we are in this concentrated transmission zone, I believe that we see a little bit higher positivity rate. If you look at the medium, then what we have found, or the environment, then 2.9% of our samples that we collected from the waterers and 1.5% of our surface samples were positive, and 3 of our air samples were also positive. Note that in that market, we find wild birds and poultry housed in the same cages. So again, we have really good chances for direct transmission from the wild birds to the poultry and vice versa. But we also have water that could be a potential medium for transmission as well. If you look by exposure, especially among the workers, 9.8% of the swabs were positive, so that's really, really high. And we're still working through these samples to really understand whether it's just contamination or active infection. And then 8.3% of the hand wipes that we have collected were also positive for avian influenza viruses. So far, our data is indicating that direct contact is really a strong route of transmission from the environment or from the birds to the humans. We sequenced some of the viruses that we had, and we found a lot of H9N2 viruses and a lot of H5N1 and H5N8, 2, 3, 4, 4 viruses, and in few of the samples that we had evidence of co-infections happening, especially in samples that we collected from the birds. So that's preliminary findings so far. Our cohort is still fresh, and hopefully by the next year meeting we'll have a bigger set of data and more analysis to share with you. So I'm going to shift gears now and discuss some of the findings that we've been seeing before this project. I mentioned that we have seen a lot of H5N8 introductions into the country, and we've been monitoring that since 2017. So we definitely are sure that we have been seeing multiple introductions because every year we see different genotypes of the viruses coming in, and we don't know, we don't think that this is any reassortment that's actually happening locally, but definitely these are evidence of multiple introductions. And when you look at the antigenic characteristics, even within the same year, you find that there is antigenic variations, and this is of concern because again, the use of vaccine is still practiced in the country. So again, the vaccine selection for the poultry is becoming really complicated. For the H7s, we've been in our wild bird surveillance, we've been seeing a lot of H7N3 viruses coming in. And when we look at them, they differ not only genetically, but they, or not only by the genetic constellation, but they also differ within the HA and the NA, even though there are the same subtypes. So we were interested in seeing whether these have any potential to cross the species barrier. And in fact, so we picked up 4 H7N3s that had different genetic constellations from different years, and we put them in chickens and in mice. And what we've seen is that these viruses that are detected in wild birds are able to infect chickens and mice readily without prior adaptation. In this table here, you see the shedding that we have detected for all the 4 viruses that we've tested in the inoculated chickens, but they also were able to transmit to contact chickens, and also these contact chickens were shedding the virus. The same thing we noticed in mice. So again, all 4 viruses that we experimented with were able to infect mice, and mice were shedding virus. What was interesting is that in the chickens, we didn't see any really signs and symptoms of disease, and we didn't see any mortality. But in the mice, it was a different story. So these viruses appear to be a little bit really pathogenic in mammalian species. So in mice, we did see evidence of, we saw a lot of signs and symptoms, and mortality were relatively high, especially for the virus that we are showing in black. So again, H7N3 viruses appear to be of concern, and I think we should start paying a little bit more attention to these viruses that are circulating in the wild birds. The last virus I'm going to talk about is my favorite virus, and I think it's Daniel's favorite virus as well, H9N2. It is really of concern because of multiple things. It's caused problems in the poultry, it causes human cases, and it's endemic all the way from Morocco into Pakistan. And we kind of tend to forget about it all the time, not to mention, or not forget to mention, that it's always the donor to the viruses that we get really scared of. So it has been in zoonotic or endemic in Egypt since 2010. It has caused only 3 known human cases as per the national surveillance system, but in our own studies, we know that at least 10% of the poultry growers have antibodies against H9N2, and the incidence is a lot higher than just 3 cases in the country. So when you look at these viruses, we know that it is endemic, but we have been seeing evidence of reassortment, and this reassortment is actually happening in the country. So it picks up genes from viruses that are being brought in from by the wild birds, and then new genotypes are happening all the time. And we've been seeing this at a really, really fast rate since 2011. So this is very concerning because, again, H9N2 is one of these viruses that a lot of governments or a lot of poultry growers do vaccinate against. So when you have all these different genotypes, and definitely when you see a lot of antigenic variations, then vaccine selection becomes an issue. And this is not an issue only for Egypt, because H9N2 is at least endemic in all the countries of the Middle East and North Africa. So with that, I will conclude to say that we continue to have issues with avian flu, not only in Egypt, but I'm sure that this would be the case for other countries in the Middle East and North Africa. We know that we have detected, or we hypothesize, that there are multiple routes of transmission that can be media for virus transmission within live bird markets. H5NX viruses continue to be introduced via migratory birds and cause outbreaks in the poultry, and then the situation with H9N2 is not really good, and then the wild bird H7 viruses are definitely of concern. What I'd also like to mention is, in our region and in low or low middle income countries, we do not have surveillance systems. So we do not have the USDA, the USGS keeping track of these viruses. So it all comes down to programs like the one that we have to provide some insight on what's really going on. And the work that we've been doing since 2008 in our region is pretty much the only program where we can continue monitoring avian influenza viruses and assessing their potential to cross the species barrier and to infect humans. The last slide, I would like to acknowledge Pam Mackenzie. I destroyed your name, Pam. Totally misspelled. But Pam Mackenzie, definitely the best center coordinator, and her team, Ashley and Lindsay, for their help with all the admin work. Kristen has been instrumental for helping us with all the stuff that we need for our human studies. James, Richard Webby should not be on this. About it. But his lab team are great. Human Link team, Becky, and the rest, and of course the people who do most of the work, which are the National Research Center team in Egypt, and they've been involved in this since 2008. And I sent 2 of my students to become Richard Webby's postdocs, and now I definitely regret that. And of course CEIRR for the generous funding since 2008. Thank you.
Time for one question before going to the break. Announcement.
Go ahead. Announcement. Right.
Okay.
Thank you.
No question. Announcement. Thank you very much, Ghazi.
Hi, everybody. Just before we go into our break for lunch, I wanted to announce our winner for the training networking event. So thank you all for participating. For those of you who went around and met people, for those of you who had the baseball cards, I hope everybody had fun. It was a really, really close competition. It came down to 1 baseball card and 3 selfies, but our duck master is Dylan McBride. So, Dylan, you're going to have to learn. There's some instructions, so go find Pam, and she'll let you know what's next, and we'll all get to watch that later this afternoon. Thanks, everybody.
We'll be back at 1:15 to continue the session. Don't linger on those burgers.
Ladies and gentlemen, my friend Kenny Cheese. Can I see? And I know just how much you're a part of me. I see you and I together. So there's nothing why to give me forever to show all of the love I have for you. And this is my reason for me to love you. I love you. I do. I'm mine, and I promise that I never let you down. The family and friends, and the Lord above, I will shall reach my love. Won't you give me forever to show all of the love I have here for you? Can be a reason for me to love you. I love you. Oh, to give me forever to show all of the love I have for you. My reason only to love you. I love you. I just
Oh, my love, tell you a tale, boy and girl, and their love story. How he loved her oh so much, all the charms she did possess. This did happen once upon a time. Things were not so complex. And how he worshipped the ground she walked. When he looked in her eye, he became obsessed. My love is like a storybook story. It's as real as the feelings I feel. My love is like a storybook story. It's as real as the feelings I feel. It's as real as the feelings I feel. His love was stronger than the power so dark a prince could have within his kingdom. Spells to weave and steal a heart.
Great. We're going to start session 4 again. This is human-animal interface and animal surveillance. And the first talk is Alexei Markov.
Thanks for the introduction. Indeed, I'll be talking about the 2009 pandemic lineage in the United States in pigs, and now I can lower this. Shouldn't. All right, so I'll be talking about the 2009 pandemic lineage in pigs and the human to swine transmission and the swine to human transmission there, and also we'll look at some risk assessment of representative swine influenza PDM19 strains there. So this is collaborative work between the flu crew at the CEIRR and the Iowa State University Veterinary Diagnostic Lab. So quick motivation here, why do we want to investigate PDM19 lineage in pigs? Important note here is that in pigs, PDM19 is not the only HA clade. There are multiple co-circulating endemic HA clades in pigs in the H1 subtype. And so, but in recent years, PDM19 became one of the major ones. And then also it's known that PDM19 evolution in humans and pigs is highly entangled, so there is some public health aspect here. And then also in general, it was already 12 years of evolution in these two hosts, so we wanted to give some update there. So this is to give you some context. This is a screenshot from Iowa State University Future tool, where they track the detections from different swine endemic HA clades throughout time. These detections in the Iowa State University Veterinary Diagnostic Lab. And so you can see here lots of diversity. And then shown, highlighted in peach color here is the PDM19 lineage. And so you can see that since 2019, it was on the rise, and it became a top 4 most frequently detected HA clades overall in pigs in the US, and it remains to be a major clade in 2022 as well. And so I'm going to give you a general review of the evolution of that lineage in humans and pigs, and this is just a small snippet so that we get accustomed to the conventions that I'm going to use. So I'm going to show you evolution and detections of PDM19 in humans using black color, and then evolution and detections in pigs using orange color. And so from this snippet, we can see some circulation of H1N1 in humans, and then a spillover event in early 2016 from humans into pigs, and about 6 months of detections from that spillover. So this is now the general view of the evolution of that lineage in the United States in humans and pigs. So this is a time scale phylogeny from 2009 up to 2021, middle 2021. So you can see that, of course, the trunk of this evolutionary tree, this is an HA tree, the main evolution is happening in the human host, but then throughout every step of this ladder-like evolution, we have many spillovers from humans into pigs. So on every step, we see spillovers of different lengths. So some of those long orange edges indicate, successful spillovers that were circulating for many years, and many of those orange edges are really short, and you can't even see them here. And so when we quantify it, we see a total of 372 independent human-to-swine spillovers that happened over the course of this 12 years of evolution. And when we look in reverse, we see around 14 swine-to-human spillovers, and we'll talk about those a little bit more later. So given this entangled structure of this virus, we wanted to look in depth at the flu season, so season by season, what is the relationship between humans and pigs. And so this graph shows that this flu season starts with 1011 up to 1920, and on the x-axis you can see the number of detections of PD-L1 in pigs, and on the y-axis the number of detections in humans. And so you can see that there is a strong linear correlation here between detections in pigs and humans throughout those seasons. And that kind of, the immediate hypothesis there is that this correlation is driven by human-to-swine spillovers. So idea is the more circulation you have of PD-L1 on the human side, the more spillovers you get, and hence more circulation of PD-L1 in pigs. And so to further support it, we also looked at temporal relationship between human and swine detections. So this is a time interval between January 2018 and November 2020. So it captures two flu seasons here, highlighted here, so 18-19 season and the 1920 season. So detections in humans are shown in blue, and detections in pigs are shown in red. And so we have those nice epidemic peaks, as always, in humans, and then detections in pigs are a little bit more sporadic, but you can see some seasonal patterns there. And most importantly, when we look at the peak detections, we see that the peak detection in pigs trail after with a lag after the peak detection in humans. So suggesting again that there is human-to-swine spillovers that offset the circulation of PD-L1 in pigs. So hopefully I convinced you that that human-to-swine spillovers drive the circulation of PD-L1 in pigs. And this is what makes the 2021 season most peculiar, as we all know that the 2021 season was a record low in terms of the influenza activity in the United States and across the globe. And so when we plot the 2021 season on the same graph, we see that it's a massive outlier here. So indeed we have close to zero detections of any influenza type in that season in humans, but then we have lots of detections on the swine side on the level of the 18-19 season, which was one of the most severe seasons overall. And so if we just judge by this regression line, we would expect that we need to have a lot of human circulation to explain this point here. And so our initial thought was, well, could it possibly mean that there was some undetected human circulation that caused this? And so what we're actually asking is, in our data from 2021 season, can we find new human-to-swine spillovers that happened within that season? So the challenge here is that as a reference, we have only a handful human sequences that were publicly available for the 2021 season, so we cannot do typical phylogenetic analysis. But on the other hand, we have plenty of nice historic data. And so we wanted to see if we can learn some patterns associated with new human to swine spillovers. And so we tried there a few machine learning approaches, but then eventually what worked was kind of a simple rule that we were able to find. And this is it. So here I'm showing you on a plot historic HA sequences, PDM19 sequences from pigs. So they were collected between 2013 and 2020. And then the sequences are color-coded here. So a red open circle represents, I think it might be a bit truncated. I'm not sure if you can see it. But so those we call same-season spillovers, and they represent kind of HA sequences that were collected in the same season as the spillover from humans to pigs occurred. So if you remember, on the global phylogeny, all the PDM19 sequences from pigs came from some human to swine spillover. And so if the human to swine spillover happened in the same season, then it's the same season spillover, and otherwise it's an onward circulation from pigs to pigs. And so this, the x-axis here is similarity of each of the HA sequences to the prior human season, and the y-axis is the similarity to the prior swine season. And so this diagonal line nicely discriminates between the onward circulation and new human to swine spillovers. And so when we plot the 2021 data on the same graph, we see that the majority of them fall in this upper triangle, suggesting that the vast majority of them, or all of them, come as onward circulation in pigs rather than new human to swine spillovers. So that basically meant that we had no evidence that there was some undetected influenza circulation in humans, but we still have this massive outlier and we wanted to explain it somehow. And so immediate thing that we see is that the prior two seasons, the 1819 and 1920 seasons, were more severe in terms of influenza PDM19 circulation overall. And so that meant lots of human to swine spillovers, but it's insufficient that there are lots of spillovers. Those spillovers need to be maintained in pigs for sufficient amount of time to contribute to the next season. And so that's what we wanted to see if that's happening. So here's a breakdown of the total number of spillovers by season. In this column, you can see the percentage of spillovers that were maintained in pigs for at least a year. And so this data, you can imagine, is biased because the longer you wait, so especially for earlier seasons, the longer you wait, the higher chance that you will pick up some longer spillovers. And so the values in the beginning can be higher than expected. But even despite the bias, we see that in the 1920 season, we had a really large percentage of maintained spillovers, higher than in the previous 5 seasons. And so that explains what happened in the 2021 season. For certain reason, there was an uptick in maintenance. So want to switch gears now, talk about zoonotic spillovers, so swine to human transmission. And I already mentioned that we detected there conservatively 14 zoonotic spillovers after 2010. And so those 14 spillovers resulted in 16 human infection cases. And if you look in the last 5 years, since 2017, it was 11 cases. And then 6 of those were reassorted. So they picked up swine endemic internal gene segments, and therefore they were flagged by CDC as swine variants. But then 5 of those that we saw were actually fully pandemic. And so we needed to rely on phylogenetic evidence to find those. So this is one of the examples of how it can look. So this is a clade of swine PDM19 viruses. So this was a human to swine spillover in early 2020. And then circulation in pigs for about a year and a half. And then 2 separate cases of swine to human spillover back. And that's typically how it looks overall, those swine to human spillovers. And so, interestingly enough, when we look at the 2021 season in particular, and the September to May interval, there were, I already mentioned that there were only a handful of sequences available from human side. In fact, there were 5 PDM19 sequences, and one of them was a CDC-confirmed swine variant. And for others, we had strong evidence that they were all also swine to human transmission. So for all the available sequences in the season, we had evidence that they're swine to human transmission. And then there were 3 more cases in September 2021. So overall, there was an uptick in the amount of circulation of PD-L1 of number of spillovers from swollen pigs to humans. And so on that note, we wanted to perform risk assessments. So we looked at hemagglutinin inhibition assays using ferret anti-CEIRR against the H1N1 vaccines. So we chose representative strains or swine representative strains to test against vaccines. So what you can see here is, so we wanted to choose strains with various lengths of circulation in pigs, so from different years of spillovers. So those are all contemporary strains, but they had various times to circulate in pigs before we picked them up. And so this spanned from 13-14 season of human to swine spillover up to 18-19. And then for 19-20, we had 2 contemporary clades, which was 2 different strains. So this is the panel. We had 6 swine strains with various internal gene cassettes, and 3 of those were associated with swine to human transmission. And so we tested them against the panel of ferret anti-CEIRR to those vaccines. And so this study was conducted by Giovanna Zanella and Catherine Young at the Flu. So this is the result. You can see here antigenic distance plotted. And to orient you a bit, on the x-axis are the vaccines, and then the y-axis is the antigenic distance. So it's a log 2-fold change in the HA titers. And so what we see is a lot of variation here, but then for at least 2 of those strains, the Kansas 20, shown in gray and green, we see that they were at least 1.5 antigenic units away from all the vaccines, and for others, they were significantly different from at least one of the vaccines. So to summarize all this, we saw a lot of human to swine transmission in the US of PD-L1s, and there was a surge of PD-L1 circulation in humans and pigs since 2018, and coupled with increased maintenance of PD-L1 in pigs since 1920 season, that led to a unique pattern that we saw in the 2021 season, where we had high prevalence of PD-L1 in pigs, despite an influx of new human to swine spillovers. And also, there was an uptick in the number of zoonotic cases. There were a total of 8 zoonotic cases, and I need to mention that 4 of those were not picked up by public health because they were not reassorted. And so that suggests that we should look at not only reassortment to understand swine origin, but actually do some comprehensive phylogenetic analysis. And so kind of the high level view is that in the 1819 and 1920 seasons, there were lots of spillovers, and some of those got established. And now for the first time, we're seeing that without influx of new human swine spillovers, there's still a lot of prevalence of PD-L1 in pigs, so it got established potentially as a new endemic clade. So quick thanks to all of us at the Flu Crew, particularly Tev Sanderson and Amy Baker, and Giovanna Zanella and Catherine Young, who performed the HIA studies. And then Iowa State University Veteran Diagnostic Lab, Phil Goger and others for contributing lots of very valuable HA sequences. And also University of Minnesota, Mary Kane also contributing sequences. And thank you all for listening.
We have time for questions.
Thanks, great talk. So if you answered this, I'll sit down again. But have you got enough data to think, so you showed this spillover, reverse zoonosis leads to different periods of maintenance in swine. If you look at when those then become zoonoses again, is there enough to make a correlation as to if they've been in swine long enough, are they just as likely to come to humans or less likely?
Yeah, thank you. Actually, they are less likely. At the moment, I think the longest time after the human to swine spillover to the swine to human spillover that we observed was 2.5 years. But generally, it's like a year, maybe less than a year before it jumps back. But so interestingly enough, those 2.5 years that what happened in September 2021, so that's the most recent data that we have. So it might be changing at the moment as well.
So you think that that's real, or there's just more of those short-term maintenance versus long-term maintenance?
It looks like there are several human spillovers that are now established as large clades within pigs, and those we see now those backwards the swine to human spillovers coming mainly from those large established clades. So.
Right, thank you.
All right, we'll move to our next speaker. This is a virtual presentation. The name of the speaker is Vijay Dhanasekaran, and the title of the presentation is Origin and Spread of the 2020-2022 Highly Pathogenic Avian Influenza H5 Pan-Zootic.
Hello everyone, good afternoon. Thank you for the kind introduction. I just want to confirm you can see my slide and you can hear me. I assume that's great then. I'll keep moving on. So I'm from, my name is Vijay Krishna, and I'm from the University of Hong Kong. My main research interests have been understanding the genetic and ecological factors that determine the emergence and distribution of infectious diseases. I very recently moved back to Hong Kong U just before the recent contract. And with my new team, in addition to responding to the SARS-CoV-2 epidemics in Hong Kong, pandemics in Hong Kong, pandemic waves in Hong Kong, we've also kept an eye on changing dynamics of human influenza, as well as since we've had manpower, especially we've recruited Sherman started working, we started looking at the emergence and resurgence events of highly pathogenic avian influenza viruses. So much of the work which I'm going to present today is done by Sherman and three great new team members. Actually, Sherman Ropang, who's a new postgrad student, and Kim, who's my project manager, who incidentally is from Memphis and is actually currently in Memphis as well. Our study really started off by observing this unprecedented outbreak. We started off in 2020, but really exploded in 2021 and 2022. So the top slide, the top left, my laser pointer, just shows the magnitude in terms of the outbreaks that's seen across multiple continents. We've seen similar emergence events in wild birds, where wild birds across multiple continents were detected, and the virus has also re-emerged into the Americas over the last 2 years. This wild bird outbreak was not just unprecedented in terms of number of birds which are continuing to die with these outbreaks, but also in terms of new species and different kinds of bird species that were infected by this outbreak, just the sheer scale across multiple continents. There's been some work which has already been done to identify the early origins of the virus. So the viruses in wild birds, which are still transmitted now in wild birds and detected across poultry, were suggested to originate from poultry that might be endemic or circulating in African regions. This is starkly different from what we've seen in previous decades of H5N1, because all the clades which have circulated outside Asia have predominantly originated from Asia just before these epidemics were observed. Coming back to the 2020-2022 epidemic, it was first detected across multiple continents, not just with bird outbreaks as well. It also caused human outbreaks or human infections, zoonotic infections, which did not circulate in humans, by the way, in many countries, and also large outbreaks were continually detected in Europe, and then subsequently was detected in North America as well. So this is just a simple phylogenetic tree of the HA gene showing these outbreaks were actually caused by two clades. One which pretty much evolved and spread to North America as well, whereas the other one appears to have restricted predominantly in Japan, Korea, in East Asia. So the spread of viruses and continued outbreaks of highly pathogenic avian influenza in wild birds especially has raised lots of questions in terms of control measures that have been adopted previously, whereas previously culling was a major strategy, and once you cull, you clear out the virus, and so you don't have a perpetuation of these viruses in poultry in these regions, and the number of outbreaks were not as huge. But with respect to happenings in the last 2 years, has really raised questions, which was considered a taboo really because of the evolutionary implications of vaccination in poultry, which is not really well understood, but which has been implicated for evolution of the HA gene in particular and antigenic advancement of the virus. And also vaccines are also being developed very actively at the moment. And also some news in terms of application might be starting in European countries already. So just to give you some background for those who are not very familiar with the diversity of influenza viruses. So we have a very high diversity of HA and NA viruses as low pathogenic viruses in wild birds globally. There's not really any linkage between the HA and NA segments. They freely reassort in wild birds most of the time. The H5 and H7 viruses are special in the sense that when they infect poultry, they can acquire a polybasic site and evolve into a highly pathogenic virus. And of these, and such events happen pretty normally, commonly across poultry systems across the world. However, most of these emerging viruses don't have chances to survive much because they just kill the poultry or the poultry is culled, and hence reinfecting wild birds and spreading globally has never been an opportunity for many of these previous clades, except the one which emerged in China in 1996 from a low pathogenic virus. It emerged into a highly pathogenic, which was detected in 1996. And the poultry system in China was quite complicated. The current situation is not really clear, but in that decade, it was definitely quite complex with multiple poultry hosts being co-housed. There was already endemic circulation of H9 N2 viruses, which Ghazi mentioned a bit earlier, and these viruses have contributed to the early evolution of the viruses within the domestic poultry in China. That's at least what the data tells us from the work which was done in Hong Kong U predominantly for over the many number of years. And we also detected that there were some evolution changes that happened in the virus which enabled the virus to infect a higher proportion of poultry sometime around very early in 2000. And at the same time, the viruses had also diverged into multiple clades, 10 clades. However, since that time, clade 2 has been the only clade which is predominantly circulating at the moment, just to I'll come back to clade 2 again. I just want to plug another important study which just came out, which was done by Nicola Hill and John Francis, Ben Stadler, and many colleagues. And they had actually tried to better understand the ecology of H5N1 because the viruses are host generalist, and most studies have either been in poultry or focused on a duck-like species, essentially. So they tried to expand our understanding using Bayesian methods. And they found some key differences between the different hosts, understanding the long-term evolution of the virus. And they found, geese and swan act as a major source population. So this goes back to the origin of the first edition of the Guangdong virus in the geese. And they donate the viruses or to other hosts. So these hosts maintain the viruses for long term. And another starting was wild gulls, which enabled their rapid, really long-distance migration. And that was quite similar to viruses which are endemic in wild gulls. And the paper also alludes to implications that gulls are naive, immunologically naive, so they can actually get infected and spread it really quickly. So ultimately, H5N1 is generalist and has a complex ecology, and multiple host species take part in their spread. So taking all this together, aims was to, there was a contrasting difference between what happened early periods of H5, and it appears to have changed recently. So we want to characterize the origins and spread of the 2020-2022 pan-zootic, better understanding the changing ecology and evolution overall, develop hypotheses on what's driving the H5N1 resurgence events, which are increasingly frequent over the recent years. We also wanted to really integrate the messy data set we have. It's not as clean as our seasonal influenza data set, and definitely not as clean as our SARS CoV 2 dataset, which is superb and quite clean, and you can get it in 5 minutes from an international database. Whereas H5N1 databases are not as clean, it's expansive, it's been collected over many decades in different formats. And so we want to actually also try to integrate the sequence data from Gizzade and GenBank with really FAO outbreak information as well as disease outbreak records in multiple regions, so you can map out what really happened during these periods. So this is just the first summary using all HA sequences. So you just get all the HA sequences and you construct your phylogenies and then you assign them to clades. And there's lots of programs now which can do it. But this plot, just a stream graph, which illustrates the major clades which have become predominant over time. Just to focus on the most recent period, we have the 2344B viruses, which are actually causing this havoc in the last 2 years. But these viruses have actually been detected as early as 2015. And these are very close related to a bunch of 2344 viruses, where in previous years, slightly different viruses were predominant. And if you want to expand this is the global dataset numbers. So if you expand this by continent, you can really see that there's only like 3 or 4 clades which had actually managed to get out of Asia and cause epidemics. And you can see this with the number of curves increasing and going down. And these actually really match with wild bird resurgence events that's happened, which is predominantly reported from Europe, but I suspect it could have happened in Africa as well as Middle East. In North America, the first introduction in 2014, it was second introduction, first introduction, it did not survive or it did not sustain within North America, and it was eradicated. However, the 2020 outbreak has been detected across both sides of the continent in multiple countries as well. So this is a large-scale phylogeny. Apologies if you can't really see this very clearly, but this provides a lot of hypotheses in terms of what really happened. Just to run through, this is the same H5N1 tree I showed earlier, but the clades which did not survive are actually clumped together with the goose grown down, whereas this expands the 2-point clade viruses. The earliest clade viruses which spread out of Asia were these 2.2 viruses, and they predominantly got endemic in African poultry for many years. However, you can see that most lineages originate from China, and there's periodic spillovers to Southeast Asia and rare emergence events across to the other continents. In terms of hosts, the most striking thing that you can see in this tree, apart from these messy, the hosts everywhere, is that most of the wild bird viruses in blue fall within really the basal positions as most of these clades which flare out, suggesting that they probably played a major contributing role in terms of spatial expansion of these viruses. But then once they seem to resurge, so looking at the most recent resurgence events on the top, which is the 2020 resurgence event, you can see that there's a lot of wild bird outbreaks, but then there's not enough time for domestic poultry here. But if you go to the previous resurgence event that happened in 2016, originated from China, it does seem like wild birds have spread the viruses, but these longer branches mainly are identified from domestic poultry. And it looks like these domestic poultry are the ones which are sustaining the viruses. And going back to the tree on the left, you can see that for the first time, these viruses actually are not settling or not emerged from Asia. Instead, they actually are poultry potentially collected in Africa, but there's only very few countries like Egypt that actually collect sustained continuous surveillance. So the specific region to pinpoint is quite hard at this moment. Another major significant event for H5N1 was actually H5N1 acquiring the ability to reassort and become predominantly H5N8, which is the yellow color viruses. But also, once these viruses have emerged, once they get back into poultry in southern China, for example, they appear to acquire the H5N6 and H5N2 N8 genes quite easily. So these two clades are actually older clades which are sustained poultry, whereas these resurgence events are actually caused by H5N8 viruses. Except these viruses have suddenly reverted back to H5N1 recently, and these H5N1s are the ones which have actually spread to the North American continent. So we constructed a spatial phylogeography analysis for just the 2344B viruses. So just a quick timeline showing that the origins of the virus is really in Asia. The timelines here are very early, before around 2000s, 2010s and so. But then the first resurgence events occurs. And as you can see that the virus starts spreading across really rapidly across these regions. Just to clarify that this model is based on, we have not used any gravity model or density models to accommodate for host density. This is just really just taking out the FAO data and just plotting them on a map. Sorry. So following the previous emergence, you can now see the branches actually not spreading really quickly for the last 2 or 3 years, but then really you can just see smaller branches jumping around in Africa and the Middle East region, with fewer jumps into Europe. And then again, later in early late 2020, you can see this virus is really exploding and spreading across the region. So now we can actually really reconstruct the spatial temporal movements of the virus over time. This particular model needs some correction, and we are ongoing it because, as you can see, there's a dot on a C here, and we were trying to accommodate the gravity model and the density models, and to accommodate the host density, especially to try and refine these better movement of these viruses. Now going and looking at the origins of these two clades, the panzootic and the JKE clades we call about, and these were all the viruses that we could find in each of the databases. As you can see that the 2020-2022 panzootic viruses, most of the ancestral viruses were collected predominantly in Egypt. But you can also rarely see one or two viruses from Iraq or Iran or something like that just across the borders of the North and Middle East. So it looks like these viruses have really been in the region for quite some time. This virus from about 2018 till about 2020 continuously in a single region. But again, being the bias and surveillance, we can't really inform that this was the origin. But there were certainly ancestors circulating around this region. Interestingly, as reported in the earliest study as well, the other clade spread to Japan and Korea was actually first found as early as 2019 in Poland, reported in a poultry farm. And these viruses again appear to have derived from viruses which have been predominantly collected not in Egypt, Istanbul, but other countries such as Nigeria and South Africa. So ultimately, clearly showing that the H5N1 epicenter is not really just situated in Asia anymore. But then we didn't measure what are the, we want to really understand what are the differences between these new clades, 2344 especially, and 2344B especially, in comparison to the 3 other major clades which emerged and spread outside. And we could really see that the 2344B viruses have actually, the diffusion rate of these viruses are much faster when compared to the viruses. And obviously, the spatial spread, the distance that the virus spread had gradually increased over time, and actually spread much further than any of the other viruses could spread. Comparing just the domestic and the wild birds of 2344 alone, we can see that the diffusion, the wild birds actually play a greater role in diffusion than domestic birds. But the range of expansion of the lineages usually occurs by domestic birds, and this is actually in agreement, but with the Nicola Hill study in cross pathogens recently. But however, we've only differentiated the wild birds and domestic birds, and we also assumed many of the cases as human samples, especially in countries where there's only human samples and there's no poultry samples, as poultry samples, just an assumption to ensure that we actually try and differentiate between wild birds and domestic birds, but also we know that most infection birds are not critical. We then looked at how the virus is spread in terms of spatial spread of the viruses. And one of the key things that we can see here again is that the spread of 2344B has driven mainly from in Europe, and unlike all the previous years where other countries have played like 2.2. Much of the expansion happened within Africa and sustained for a really long time. 2321 viruses predominantly in China, but again mostly in Asia, sustained in Asia. 2344 a similar pattern, whereas 2344B viruses have a reverse plot. We tried to find out where was the major spatial linkage of these viruses, and we were able to find that there's geographic proximity is a major driver of spread. So if there are viruses that are endemic in poultry in Western Asia or Africa, is obviously this is going to cause a much larger numbers of resurgence events, just because these are under major flyways, unlike places in Southeast Asia or South Asia, which are not in a major flyway zone, such as in West Africa or in countries surrounding Asia. We also compared how the roles of the different hosts change between these clades, and I think one of the most starkest things was that wild birds play a major role, unlike all the other clades in terms of their transmission patterns. And these plots just illustrate that plot. In this again is a work in progress, so apologies for having humans here. We could have actually decoded that to domestic birds for this particular analysis. Finally, everybody loves the assortment, there's some very patterns. Sorry?
Sorry to interrupt you, but you need to wrap up.
All right, that's my last result slide. So the main conclusion for the reassortment patterns is that the most recent 2344 clade viruses have a greater propensity of reassortment. You can't really see this here because there's lots of reassortments happening all along the evolution of these viruses. But the earlier 2321 and 22 clades, you can see that these viruses have actually much lesser splits. You can see just 2 splits here, unlike the 2344 and 2344X viruses, which are quite a lot. And these are just summarized in this plot here, again showing that 2344 and 2344B have a greater propensity of reassortment in many genes. So finally, to summarize, this is a lot of repeat of what I've just said earlier, but there's some questions in terms of why is there an increased propensity for reassortment of these viruses, and does the HANA linkage have something to do with this? Is it ecological? Is it a host factor? It's not really clear, and there's lots of research going on in this area, especially about the molecular aspects, but not really in terms of the ecological aspects of these viruses in terms of driving reassortment. And I think that the relaxation of the HA and the NA reassortment may actually enable the reassortment of the other genes and segments as well, because there's much lesser restrictions of the viruses. We've learned a lot by genetic analyses, but we don't really have the implications of specific control scenarios of taking this forward to identify specific control scenarios, and this is going to be our ongoing work. Thanks so much for the time.
All right, unfortunately, we need to move on to the timing. So the next speaker is Wendy Puryear.
I'm getting there. It's giving me a little bit of attitude up here. So we're having some technical difficulties. It is, it's just this, it's not synced.
All right, we seem to be synced up now. So I'm excited to talk to you today about some of our work at the Avian Marine Mammal Interface and why we continue to think that this system is a crucial one for continued study. So starting with the question of why seals. For the first half of the talk, I'm going to really just kind of set the stage of giving some baseline information of influenza in seals, and then turn the focus over to the recent incursion of high-path H5 into North America, with an eye toward interspecies spread and mammalian adaptation. So focusing in on the species barrier between avian spillover into seals, we certainly know that there is a lot of influenza that is in water birds, and there are ample opportunities for transmission between birds and seals. And in fact, pretty much all of the influenza that has been characterized in seals to date really has traced back to waterfowl. We know that there are diverse subtypes of influenza A that can be detected in seals and influenza B. And here we're looking at a polar depiction of some of the well-characterized incidences of influenza in seals around the globe. So initially, a lot of the cases of influenza showing up in seals was really in the Northwest Atlantic. So dating back 50 years, we were starting to see an assortment of subtypes that have been defined in that region. To date, there have been 6 distinct subtypes that we have detected in the Northwest Atlantic. And I am hearing a crazy echo. Is that echoing over there for all of you? Making you crazy? Okay. Just making sure I'm not jotting notes out there. So we've had 6 subtypes that have showed up in the Northwest Atlantic. And pretty much all of those have been associated with mortality events. And then about 10 years ago, there started to be some additional subtypes that have shown up in the Northeast Atlantic. And just recently, we're now starting to get influenza that is showing up in the Pacific. And if I can do a quick plug here, if you want to come by poster 153 tonight, I will be happy to tell you more information about a new subtype that we've identified in harbor seals in Alaska. So in addition to these transient outbreaks that have occurred over the last several decades, we've also had the opportunity to do active surveillance in apparently healthy seals on rookeries, gray seal rookeries off of the northeastern United States. And at this point, we have studied about 1,000 gray seal pups over the span of 10 years. And looking in that population, we've detected each year, and again, these are apparently healthy animals, we've detected the presence of influenza in those seals every year. And there's been variability from year to year. Overall, it averages out at about 10%, but we continue to keep picking it up there. So this tells us that either there is influenza that is continuing to circulate in that population, or we're having very frequent regular spillover from birds into seals. But either way, they're clearly permissive to virus coming into those populations. So we've been able to look at serology from the same population. And at this point, we're just shy of 100 seropositive samples, 99, one more. And have been able to take that sera and to look using hemagglutination inhibition assays against a panel of subtypes of influenza and see whether or not we're getting recognition by the antibodies in the seals of those subtypes. And again, there's a lot of ebb and flow and changes from year to year, but really the take-home message from this slide is that we do detect a breadth of antibodies against a number of different subtypes of influenza over the years. Again, these are healthy animals as far as we can tell. So again, suggesting that there is regular exposure of influenza in these populations. So in addition to the fact that we have this regular detection of influenza in these populations, we're also talking about a scenario here where we have an increasing number of animals and an expansion of the host range. So just focusing in on those gray seals in the Northwest Atlantic stock, over the last few decades, there has been an exponential increase in the number of animals that are there as they've recovered after the Marine Mammal Protection Act. And just to give you one quick example of the expansion of range, so showing you here a map of the 3 primary species that we see in the Northwest Atlantic, focusing in on the gray seals that are shown there in orange. That's the habitat range that has been traditionally defined. Just recently, some of our colleagues who work down in Delaware have noticed that there is a new colony of gray seals that have set up down there and are actually having pups in that area. So that is something that has not been seen before. And although you get the occasional animal that migrates down, the fact that they're setting up a colony and having pups there really shows that they're starting to expand that species range in addition to getting a higher number of animals as the population recovers, in addition to having all of this regular detection of influenza in the population. And then again, just really briefly, by doing work with rehab facilities and network that we have along the entire East Coast, we've been able to, in addition to that active surveillance, also keep an eye on what's going on in animals that come in through the stranding network. And even though we had been detecting influenza through that active surveillance out on the rookeries and the healthy animals, over the course of time we've been doing this work, dating back to 2013, we hadn't detected influenza coming in through the stranding network until a few years later. So they were always coming up negative. And in 2015, we had our first detections of influenza in harbor seals that came into the stranding network. And then it was a few years later that it also expanded, that we started to detect it in both gray seals and harp seals as well. And it's bounced around across the years, but we've continued to detect in all 3 species since then. So this brings us to the current high path H5N1 outbreak in the Northwest Atlantic. So basically, all of the pieces were already there for both the virus, but also the good news, also the rapid response. So we have a reservoir host. We have a lot of water birds, clearly, that are in that area along the coast of the Northeast United States. We have a susceptible and plentiful species that appears to be perfectly happy to have influenza infect it as a host. And we have a heavy overlap between these 2 different species. But the good news was that we also had a well-established infrastructure throughout the stranding network where we were able to quickly start to look at sequences and samples coming off of these animals